record. Okay, cool. So obviously the first thing you need to do is open Quartus. And if you guys have questions at any point, just let me know. And have y'all used Quartus before?
I have, but it was a very, like, I don't know what version it was. It was much older than this, so
Okay.
things have changed a fair bit since I used it.
Okay. Well, cool. So I'm gonna talk through everything I do, and if I get too low level, let me know and I'll speed up.
Okay.
So you're gonna click the new project wizard. Next, here's something that I find helpful. You never want to save your project in the working directory where you download Quartus. It can cause Quartus to hang and have issues. So I'm just gonna go to my desktop for the sake of this tutorial and make a new folder called microarray tutorial. You guys can, choose whatever place you want to save these files in. And I'm gonna call this project tutorial. Empty project is typically what you want, and I've never added any files. For our board, if you click the first name and scroll down one, that's our board. If you ever forget what device you have, you can look on the quick start guide. It's the first bullet point under hardware. This came with your FPGA starter kits. So if at any point you forget what the device is, it's right there. But it's the second one on the list when you pull up the ARIA 5 family. So. And then next, we're not going to do anything with the EDA tool settings, and then finish. So this is going to create a new empty project. So the first thing we're going to do for this project is we're going to instantiate a ROM block using the IP catalog. So over to the right, you should see the IP catalog. If for any reason you ever exit that, you can go to View, Utility Windows, and select the IP catalog from this drop-down menu. IP is intellectual property, so these are just predefined function blocks that Altera provides. So they have a ROM block 1. We are going to use the ROM 1 port. I'm going to call it wavetable to make sure it's in Verilog. And okay. So the wavetable is just a list of hex files or of hex data that is a first half of a sine wave. It's the top hump on above the x-axis. So that's where we're using ROM because we just want to read from the table. There are tons and tons of IP blocks, and you guys are going to be using probably many of them for this project. So all of the IP blocks pull up the MegaWizard plugin. It is going to look different depending on which IP block you choose. Obviously, there's going to be different parameters and settings. Our wavetable, I just posted in the Slack, but we have 1,024 8-bit words on our wavetable. So we want to change those settings. I'm going to leave these the way they are. I'm not going to do anything to this page either. And then here is where you add the hex file that has your wavetable data. So browse. I stored mine on my desktop. You want to make sure that the hex file or any file you're adding is in your project folder. So I'm going to add it to the folder. It will cause issues if you don't have it in your folder, so just keep that in mind. Next, not going to do anything there. I like to create the instantiation template files when I create my IP blocks. This personal preference, I'll show you what those look like in a second. You do not need this. All you need is the black box file. And then we'll click finish. And then this is just adding it to the project. Yes. Okay, cool. So now we have the ROM block and it has all of the wavetable data. So we're going to make a new Verilog HDL file to actually access the wavetable. And I'm going to create a very simple module for this tutorial. We're going to have an input clock and an output wire that's 8 bits, and I'm going to call it dout. You guys can get fancier, but for the sake of the tutorial, we're going to keep it very, very simple. And then after I declared those, I'm going to have a 16-bit wire that I'm going to call, that is not how you do 16 bits, 16-bit wire that I'm going to call output frequency. This is the output frequency of the sine wave I'm going to simulate. I am going to declare it as 1000 right now, so I'm going to have a 1000 hertz signal. You can change this. It'll change some math. but that's fine. I'm also going to have a 16-bit wire that I'm going to call M, and I'm going to assign that to the output frequency divided by a 16-bit digit 15, decimal number 15. So M, if you remember from the lab, is the step amount, and that's how much it accumulates the address of the wavetable to get the data. And so this is a nice way of doing it because I can change the output frequency and it'll just change the step number. Okay, so I'm also going to have a 10-bit register called address and a 16-bit accumulator register.
Oh, excuse me, what is the M?
M is, it's the step size. So if you read the lab, basically what it does is like, if you want to change the output frequency of the wave, right? So by default, if every clock cycle you read the next data point, you will get some output frequency of the wave. If you want to change that frequency, you can change the data points you read. If you read fewer data points or more data points, you can therefore manipulate the output frequency. So M is the step size. So it can be like 5. So you could read every 5th data point, or it could even be like a fraction. So you read the same data point multiple times. And the lab talks a little bit more about that, but that is what M is. It's that step size. And we don't have to know exactly what that is. And I'm not gonna go in the tutorial into this math. I guess I could if you guys are interested. But basically I found if you divide the output frequency by 15, that works for frequencies 100 to 1,000 to 10,000. Okay, I'll move on. So we're gonna have our address and accumulator registers. I'm gonna have some initial statements and just go ahead and initialize these to 0. Just so there's not any junk or anything, and I know what's going on. And so now we're going to actually accumulate the address in order to access the wavetable. So we're going to say always at the positive edge of the clock. The accumulator is going to be less than or equal to the accumulator prior plus the step. And the address is going to be less than or equal to, if I can type, bits 14 through 6. Okay. So I am using bits 14 through 6 of the accumulator because that's 9 bits. I want to use bits 15 through 6. The reason I am doing only 14 through 6 is because I'm going to use the 15th bit, the most significant bit of the accumulator, later on in some logic. So I'm not going to include it in the data right now. This is the way I have found to do it. There might be different ways to simulate a sine wave, but I'm going to use the 15th bit to signal whether I need to be above or below the x-axis. And so that's why I'm not using it in the address. So instead I'm using bits 14 through 6. So then this is where the instantiation file from your ROM block comes in. So I'll show you what that looks like and why I like it. So it's automatically put in your project file and you can open it. And this is what it looks like. And it's basically just showing you how to call this function. Now for this ROM block, it's pretty easy. Like it has an address, a clock, and an output. So you don't really need the instantiation file for this. Different IP blocks, the way you call it and the different signals, it can get kind of long. So I just like to have the instantiation template. Again, this is personal preference. It doesn't actually do anything. So I just copy it and paste it in. And then I change the settings to what I want them to be, or the variables to what I want them to be called. So our address is called address, our clock is called CLK, and our output is called DOut. Okay, so what this program does right now is that at every clock cycle, the accumulator is increased by the step size, and the address is taking some of those accumulator bits to address the wavetable with the same clock and output DOut. So I'm going to show you guys right now what this looks like, and this is going to be what data is contained in the wavetable, and I'll show you that it's only above the x-axis right now. It's only half of a sine wave, but I can show you guys what that looks like right now. It might help you understand the further logic I do to kind of manipulate the sine wave to actually look like a sine wave, or the wavetable data. So here I'm going to put my test bench. I always put my test bench on the same file that I declare the module, because I think that's easier for organization. You can create a separate file if you'd like. The first thing I'm going to do is declare the time scale. You pretty much always want to do this in test benches. I've found, and then I'm going to create a tutorial test bench module. We're going to have a register called clock and an output wire that's 8 bits called dout. Then we're going to call our tutorial and input the variables. We're also going to have some initial statements in here as well. Clock is going to be equal to 0 initially. Okay, so this is how you wait for a certain amount of time. So this like $ means wait, and not $, sorry, hashtag means wait. I have arbitrarily chosen this amount of time to wait. This is typically how long I wait in all test benches. You can use a different number. And then this $stop just stops the test bench. This is just a nice way so you don't have, it doesn't go on and on and on and on and on. Anyway, and then we are also going to create a clock. So always at wait 50, clock is going to be equal to not clock. So this is going to create a square wave that just simulates a clock. And in the module for that. Okay, so let me make sure I have everything. I should, yeah. All right, so does anybody have any questions thus far?
So just want to make sure the initial statements only works for the simulation, right? It doesn't go into the FPGA implementation.
That's a good question. I think it does go into the actual FPGA implementation. I would have to check on that, actually. I don't know. I just know that it's it only happens once when the program first begins, and it just initializes variables to whatever they are. Good question. I don't know.
And also the unit of the numbers, like the hashtag 50 and hashtag the 1245, the unit is just the time scale, right?
Yeah.
Okay.
Yeah. Okay, so I will go ahead and save this. A good thing to do in Quartus is you always want to save your file to be the name of the module, the main module. And then since we're simulating, we don't need to do a full compilation. We only need to do the analysis and synthesis. So I will go ahead and do that. Hopefully I don't have any errors, but I could. We'll find out. And simulating is always nice because it takes like 1/10 of the time. Yeah, okay. So I can actually set these equal. There we go. I'm actually assigning them now. Is there anything else? Save the changes. Yeah, when you assign variables, actually use the equal sign. Pro tip. All right, looks like we're good. Okay, so if you have never used ModelSim before, what you're gonna need to do for the first time, and you only do this once, I've already done it, but I'll show you. If you come to Tools and Options, EDA Tools, Tool Options, you need to link the executable, the directory that holds the executable of ModelSim, into the ModelSim Altera box. This is the typical path for Windows. Linux has a different typical path. You can Google it and find it pretty easily. Once this is set up, you never have to do it again. But this is how it knows to open ModelSim as your EDA tool. So, okay. Then we're going to go to Tools, Run Simulation Tool, RTL Simulation. The first time you open the project, it's going to ask what language. We're using Verilog. Okay. And ModelSim will pop up eventually. Here we go.
So does Quartus, I guess, it automatically finds the test bench? I don't know, because like the Quartus version I use, you have to specify like what file the test bench was in and all that.
Yeah, so you still have to do that with this too. And I'll show you, like right
Okay.
now, I'll show you how that pulls up. So this is another little hacky thing I do. If you guys find a better way to do this particular thing, please let me know. When you use IP blocks, you have to tell ModelSim the library it needs to be able to run those IP blocks in the simulation. So the way you do that is you go to Simulate, start simulation, and then come over here to libraries and which libraries it needs to search to be able to run those IP blocks. Different IP blocks use different libraries, so you're gonna need to make sure you know which one you're using. The ROM block uses the Altera MF var library, so we'll select that. You can add as many as you want for as many IP blocks as you want. I know off the top of my head that PLL uses the Altera LNSIM var, but you probably have to look those up. So you do have to add this library in every time you open ModelSim, which can be quite annoying. So like I said, if you guys figure out a better way how to do that, let me know. Then you come to design, and this is when you specify your test bench file. So if you expand work, I'm gonna choose the module tutorial test bench. Okay. And then I always have this wave view open. I don't know if that automatically opens. If it doesn't, you can go to view, wave. Okay, so it loaded the design. You can look down here for errors, but it loaded correctly, so we're fine. You want to right click on D out because that's our output sine wave, add the wave, and come over here. So we specified it to run for that arbitrary amount of time that I use. If you come up here, you can click run all. And that's what it's going to do. It's going to run the tutorial. It waited for this amount of time, and now it's at stop. So you can come back to Wave. If you right-click the data, you can view it in different ways. If you come to Format, Analog, Automatic, this is going to be the sine wave view. And as you can see, we're only seeing a small little chunk of this test bench. So we can come up here to Zoom Full and see the whole thing. So this is what the wave table looks like. It is just the first half of sine wave. So now I'm going to show you how to kind of manipulate the data to get it to basically flip over the x-axis when the accumulator most significant bit is 1. So that's, again, why I didn't use the 15th bit in the addressing. So exit all this. Go back to tutorial. All right, so one thing is this ROM block, it has to have a wire. It has to print out to a wire. So I'm going to use like a temporary wire up here. I'm going to call it dout temp because I'm going to do some manipulation to it and I want my actual output to still be dout. And then since you can't do manipulation or variable assignments with a wire, I'm going to declare a register. I've been calling it switch because that's kind of what I thought about, like switching the pump. It might be more of a flip, either way. So always at the positive edge of the clock. If the most significant bit of the accumulator is 1, we are going to do some logic, and then if it's 0, we're going to do some logic. So this is how I do it. This is kind of, it's kind of hacky. So I'll explain after. Let me type all this. So what this is saying is if the dout temp, which is what we're printing, that's the data we're getting out of the wavetable, if bits 6 through 0 are 0, or if you take bits 6 through 0, make them negative. If they're all 0, you're gonna want to assign switch to an 8-bit 0 number. This is just because at some point when you're doing the flipping, if you don't assign this, you get a weird outlier. So I've included this. Otherwise, when the accumulator most significant bit is equal to 1, you're going to concatenate a 1-bit binary 1 and negative dout bit 6 through 0.
So why if you use negative dout 6 through 0?
Yeah, so this is gonna be the flip over the x-axis, right? So you're making it negative because you're flipping it over the x-axis. Yeah, good question. And then you're just reassigning the first bit to 1 because, again, we're using the most significant bit 0 to be the first half and 1 to be the second half. And so that's why you're doing that. And that's why we're using the 15th bit of the accumulator to determine when to do this. And then if the most significant bit is 0, switch is going to be the concatenation of a 1-bit binary 0 with positive dout temp bits 6 through 0. And then finally, we are just going to assign dout to be equal to switch. So that's why we declared the temp wire and the switch register to do this logic. And yeah, so basically what this is saying, again, is when the accumulator's most significant bit is 1, we want to flip over the x-axis, and that's what this is doing. Otherwise, we want to get the same data that we already had. So that's what this is doing, just reading the first hump of the wavetable. So now we'll do analysis and synthesis on this again, and hopefully I do not make any errors. I, of course, did make errors. Oh yeah, double equal.
Oh, I think the dout on line 36 should be dout temp. Right?
You are right. Good catch. Good catch. Thank you. Awesome. Okay. So then again, we're going to go to Tools, Run Simulation Tool, RTL Simulation. And it'll pull up ModelSim. And then Simulate, Start Simulation, add in the library that the IP block needs, Design, Expand Work, Tutorial Test Bench. Okay. It'll load the design. Right-click dout and add the wave. Come over here, run all of it. It'll let you know that it's stopped. Right-click, format, analog output, and zoom out. And that did not work. So let's go back and see what happened. Let's see, what did I do? Always at the positive edge of the clock. If the accumulator 15, negative dout bit 6 to 0 are 7 bits 0. Switch is 0. Otherwise, go 1, negative dout bit 6 is 0. Oh. Else, switch this. Okay, let's try this again. If it doesn't work this time, then something's wrong. But it should. Okay. Also, you have to close ModelSim if you want to reopen it. So it's a fun fact. Tools, RTL simulation. Start simulation. Add the library. See, isn't this kind of annoying?
Yeah, a little bit.
So excuse me, how do we know what library we need to use?
Yeah, so you're gonna, okay, well, you can either Google it or down here in this block, it'll say, so actually, let's see if I delete this, if I can show you. So you'll see it has some errors loading the design. And I think maybe it won't show you what library you need. See, it says the instantiation of alt-sync RAM failed. And I guess you can Google that and find the library. I'm assuming that's what I did. Okay. That would be nice if it told you the library. But basically, if you don't have the library, you will know.
Yeah.
Okay, cool. All right. Right click, add wave. Hopefully this works this time. That was such anticlimactic letdown. Zoom all the way out. Format. Yay! Okay, so now we have this beautiful sine wave. And so this is just how to read the wavetable, and now we can start doing some actual manipulation to the signal, create another output, and compare the signals. But yeah, so this is a very basic tutorial. I will send you guys this code, and I've sent the hex file, but I will also include that when I post this video. So I'll include everything. I'm going to make a blog post on my blog and post all this and send you all the link.
Okay.
And yeah, so there you have it. Very basic tutorial on how to read data out of a wavetable and simulate a sine wave. Any questions? And again, if you want to change the M number or the output frequency and stuff, you can look at the lab to get the math for that. Of course, we're going to be using ultrasonic waves, so in the future we'll probably need to change that, but our microphone is not ultrasonic right now.
Can you explain the first line, like in the when we're doing the flipping, the first if statement, like if negative D out. So if the negative D out of like the first 6 bits equal, like if they're all 0, is what you're looking for?
Yes. So I'll just show you what it looks like if you don't have that in.
Okay.
That might be kind of a hacky way to do something. So let's see. I'll just remove this, and will that work? If commutator switch is also needed with combination. Okay, cool. So it makes like a really weird outlier data point. And this is just how I've found how to fix it. Oh, it's because I have ModelSim open. See, it does this weird.
I think maybe it's because if it's 0 and you concatenate a 1 before it, it will become 1 0 0 0. But then it's the most negative number in two's complement, so because two's complement do not have negative 0, so the value falls down to the smallest.
Right.
Yeah.
So in order to just, you're right, we want it to be 0. Yeah, exactly. So that's the way I have found to do it. But yeah, you're right. So yeah, I guess you could keep it. I don't know. It's kind of a cool, I don't know. Don't keep it. Alanson would not be happy. He'd be like, your sine wave looks weird. Yeah, any other questions? That was a good question.
So I wonder, what is a wavetable?
Yeah, a wavetable, it's just kind of a fancy word for just hex points from a first half of a sine wave in a table. So they call it a wavetable because it's describing a wave. But it's just a table of digits of data that you can use to make a wave.
So can it generate other waves besides sine wave?
So you can do some manipulation and get some other, yes. Yeah, I can show you. Yeah, I've created that. I wrote a paper on that in undergrad that I can show you if you're interested. But yeah, you can do like sawtooth, triangle, square. Yeah, you can do some different waves. We don't really need those, but yeah, so you can just do some different manipulation with different addressing and stuff. Let's see. Okay, well, awesome. That's all I have for y'all. Like I said, I'll send you this code, and you guys can begin playing around with it. And there's a CIC IP block, so that's going to be the first task, is get that IP CIC filtering working. I don't know how difficult or easy that's going to be. It might be as simple as, you know, adding in the ROM block and just it works, or you might have to do some weird manipulation. I've never used a CIC IP block before, but that'll be the first step. And yeah.
Okay.
Awesome.
Thank you.
Yeah, no problem. And I will have office hours again tomorrow if you guys start playing around with this and get confused.
Yeah,
okay.
Absolutely.
Well, thanks. Thanks for coming.
Yeah, no problem.
Bye, y'all.